In this video, we're going to be talking about successive loop closure for our longitudinal dynamics. And this will allow us to control altitude and airspeed. And we'll be able to go through this a little bit quicker than the lateral dynamics or lateral control because it's very, very similar. So one of the first differences, though, for our longitudinal control is depicted in this diagram right here. So when we take off, when we're in the takeoff zone, we're going to have a fixed value for our theta. So we're going to just control theta to some desired fixed value. Once we're out of our takeoff, once we've achieved a sufficient height, then we're going to continue to rise, but we're going to saturate our height command. So our height command is going to be saturated based on our current height. So this is the current value. And the maximum deviation. Maximum command deviation. So while we're in that regime, we're going to continue to rise to our desired altitude, but we're not going to command the desired altitude right off the bat. That'll do a couple things for us. One, it'll avoid a bit of integrator windup, right? Because as we are trying to go all the way up to this desired height that's very high compared to where we started, that integrator is just going to be winding up the entire time. Second, and it's going to have if we look at the area, right, we have a huge amount of wind up. And second, the other thing it's going to do is going to help us to avoid having our pitch angle get too large. So we're going to regulate, it's going to make it so that we're not trying to pitch up all the way and shoot off like a rocket, because most of our small unmanned aircraft aren't able to do that. Okay, so we'll regulate our height command, and then once we're operating around our nominal height, then we just are basically giving our command, our height command to the aircraft as it comes. Okay, and again, we implement that. Really, the only switch is at this height takeoff, right? So when we're first taking off, we're going to be at a fixed pitch. So let's talk about this altitude hold regime or command. So we're outlined or circled in blue is the inner control loop. So again, we have, if we were to look at this, these are the dynamics that we saw. This is the model from chapter 5 for our pitch. And then the rest of this is now our control, our inner control. So C1. So this is the innermost control. And you see that we're actually choosing one of our control values as well. We're choosing the elevator command. So let's jump into the pitch hold. One thing that we notice here that we didn't put in the previous, this is just a saturation function. And in reality, we should have that in all of our commands. We can never command, so this is basically our max, and here's our min. And so if our command is between the maximum and minimum, we'll allow it. If it's above it, then we're just going to threshold it at either the max or the min, right? And this saturation function should be in all our controllers. Excellent. So we have that saturation command. What we're going to do is just ignore it. So pretend it doesn't exist. So for all of our analysis, we just ignore that saturation command, but it is there. And then we have our loop, just like before. We have we're designing our PD control, and we have a second order system. The one difference between this second order system is that we have this DC gain. So this is a DC gain that we didn't have. And we'll see that that slightly changes what we do from our nominal successive loop closure, but not by a huge degree. And then if we're given our natural frequency and our damping ratio, then we can calculate our gains. So we have our second order system, and we can still calculate our gains from our damping ratio and our natural frequency. So in this control regime, our design parameters are that natural frequency and damping ratio. And then we have this gain, which is different from before. Now, we could fix this gain. We could fix using an integrator. But again, for the inner loop, that's a bad idea. We don't want to introduce the instabilities or additional dynamics in that inner loop. So what we do is, instead of replacing this, so previously this had been we assume a pass-through, but now we just, if we're given a theta commanded, it's going to end up being, the theta is going to just be equal to our DC times our commanded theta. Okay, and so we'll just deal with it in our outer loop. So again, so that's stating the same thing. So now if we simplify it, this is basically the result of the inner loop. We have that DC gain, and we're going to come through and we're going to design our control again. So if we look at our theta super C, it's going to have this integrator term where we have the error between our commanded height minus our height. And remember that our commanded height is saturated as well. Anyway, so we have our commanded height, plus we have then our proportional gain times our commanded height minus our actual height. So that should look very similar to previous. So the cool thing here is that now, since we added this PI control, it's going to help us go to that steady state. It's going to help us get rid of any of the steady state error, including the error that comes from our constant DC gain. So it'll help, that integrator will help us avoid any of the steady state error from that constant gain, and then we're good to go. And we also account for that gain when we're looking at our damping ratio and everything. So if we come down here, we again have a very similar formulation. The biggest thing to notice is that our natural frequency is of the outer loop is again dependent on the natural frequency of the inner loop. But given our natural frequency and our damping ratio, we can again calculate what our gain should be. So the design parameters now are our W sub H and the damping ratio zeta sub theta. Okay. Excellent. So now we'll go to our second control law. We're going to control our airspeed using throttle. So again, we have the one difference on this one. Again, there's always the slight differences, right? Just recall that our bar notation that we had VA bar is just equal to our actual airspeed minus the nominal. Okay, so the bar notation is from the nominal. Maybe I should write deviation from the nominal. So we have a deviation from the nominal, which we assume is going to be somewhat small, right? And the thing to notice is that this bar notation comes in a couple different spots. The original slides didn't have the bar notation, but they should have down there, right? And so we have our bar notation there. Okay, so we have this now, this transfer function again, and we have a second order system. So we're designing this PI control again. So another PI control to determine our deviation from our nominal throttle. Okay. So again, we do the same trick. We just look at our transfer function, and we now have, again, we have a 0 up top like we did on our in a previous controller. But now we have the gains we get to choose are our natural the things we choose are our natural frequency and our damping ratio. And from that, then we can calculate our gains again. So very similar to before. The one thing that I want you to keep in mind is that once we obtain, so our control gives us our deviation, and so you better make sure that you actually add in the nominal, right? So this is going to end up being your actual control law. So where we have this nominal term, oops, I meant to circle that in a different color. Where our nominal term shows up. So that's basically, this is like our feed forward term from before. From the, I guess it was the course angle command loop. And in actuality, if you don't have that that feed forward term, again, the integral can learn it. So the integral can learn this. The integral can learn, but it will take some. We'll add, and this one is even more important than the roll angle. It'll add some nasty transients. And I just noticed here, just barely, that this should be an integral, right, from our T naught to T. Okay, so we have the ability to learn it with our integral, but there's really not any reason to allow it, especially because we will always get that from our trim trajectory design. Okay, so a summary. So our inner loop is going to be for one of our first, the only inner loop we have, I guess, in this one is our pitch attitude hold. And we then have our pitch angle is one of the design parameters, and our damping ratio. And then we have our attitude hold, and recall that this helps us define, this is defined in terms of the natural frequency of the pitch loop. And then for our, so this is control loop 1, and then we have our control loop 2. Hold on for just a sec. Sorry, it's got thrown off just by a bit. We did not go over the airspeed outer loop, but then we did talk about the the throttle loop, right? So we do have that. So this is our second one that we talked about. Okay, excellent. And then again, similar to before, those are great starting points for your control, but here we can then come in and in flight start to tune these gains to get to your desired step response. Excellent. So now that ends our two different controls, both our lateral and longitudinal successive loop closure controllers.